Okay, so we're starting the recording. Hello, students. This is ICS 6D. I hope you are doing well. And today's topic will be solving recurrence relations. I believe that sections 8:15, 8:16 in the textbook. Okay. Let me go to the presentation. Share screen. Okay. Yes. Let me change the. Okay. So let me jump to it. We know that recurrence relations define a sequence, right? So we have dealt for now 2 weeks at least with all sorts of recursive behavior, recursive algorithms, recursive definitions, recursive definitions of sequences in particular, right? And in all of them, you had a system of this nature where you define some base cases and then you define instances of here a sequence at some index in terms of the values of the same object, a sequence at smaller indexes. Okay, so for example, this is a recurrence relation, right? And we had examples of Fibonacci. We had other examples of this, right? Where this would naturally come out as, for example, running time of a recursive algorithm, right? Where like a running time with some input is related to a running time on smaller inputs. And as you write out these recursive relations, you can say, well, what is the closed form for this? So for example, for this particular, so a closed form, right, is how does it differ from the recurrence relation? First of all, well, this is an example of a closed form expression where the right-hand side does not make any references to the sequence itself, right? You can evaluate this this formula as a function of n itself, and even if n is a million, you don't need to evaluate this for previous, and you don't need to make these recursive calls to evaluate, right? You have a closed formula to evaluate. I guess I'm saying battery. So the question, of course, is like, how do we get from the recurrence relation like this to the closed formula, to the closed form expression for the sequence? Because that's what we want, right? So we know that so far in the class, right, we were basically given a closed formula for a sequence. And we saw that induction is a very convenient tool to verify that the formula closed form is correct. But that doesn't really tell you how do you derive this, this closed form formula in the first place. So this would be what today will be about, okay? We will show how to derive these formulas for a certain class of recurrence relations. In the lecture, I will only talk about a more restricted class. In the reading, you have extensions to larger classes. Okay. Okay. But still, we don't cover everything. So the class that we will see how to solve is called linear homogeneous recurrence relations. So here is what this term means. Sorry about this. So in this example, you have a recurrence relation where Gn is defined in terms of previous two elements of the sequence, right? So the n minus first element and the n minus second, and it's some function that takes 3 of these and 2 of these, and moreover also has some expression that involves just n itself. For example, if the recurrence relation, okay, so we call this a linear expression because it's linear in these variables. So if you just look at this expression as some function of the variables which are previous elements of the sequence, you ignore this term, and look, what kind of function is it? Well, it's a linear function because it takes this value x, argument x, and argument y, and just applies some constants in front of them and adds them. And these are linear operations in the sense that if you were to plot this on a xyz line, where this is x, this is y, and this is z, it will be a line, right? So Gn grows linearly with Gn minus 1 and Gn minus 2. By contrast, this is a quadratic equation, right? So if this is your argument, Gn minus 1, then Gn as a function of that argument is a quadratic function. It is a linear function of this variable, but that doesn't mean that the whole thing is linear, right? Like this one is and this one isn't because this term isn't. If you multiply 2 of these previous elements of the sequence, right, you also break linearity, because if you were to plot, this is your z, and this is your x, and this is your y, this will be z equal x times y. It would not be a line in a 3D space. Or any dimensional space, because this is sort of a coincidence. I'm explaining this for the case of recurrence relations which have only 2 previous terms, but everything applies whether you have 1 term or you have 3 or 5 or any number. Likewise, this one is not linear because, because basically this is not a constant. Okay. So this is the notion of linearity which we mean here. And what's this homogeneous part mean? It just means that the recurrence relation makes no reference to anything but the previous elements, right? So it doesn't have any additional terms that are a function of n. So this recurrence relation is homogeneous, and these two are not. Okay, like these are basically somehow shifted by some term that is not a recursive term. Okay, and just to cut the chase, we will talk about how to solve these types. And we don't really have much to say in the textbook, at least, about how to extend it to this kind of quadratic or these type of relations. In fact, we haven't seen an example where this would be useful. So, if you had a recursive algorithm whose running time on n was quadratic in the running time on just one previous, that would be a disastrous algorithm. It would eventually terminate. But just think like what this sequence really would be, right? It's gonna grow like hell. Okay, so sort of no surprise that if you have a case of something like this in the analysis of an algorithm, run and try to create a different algorithm, right? So that's why we are not spending much time on analyzing these. On the other hand, these things will come up. These are basically, this is a recursive structure of your algorithm, like search, fast search, power, fast power, all these examples, right? Has this nature. Okay, in order to solve any instance of the algorithm, you have to solve some number of previous instances, and if you're lucky, it's just 1. But perhaps there is some fixed costs to what your recursive algorithm does in a sort of post-processing. When it returns from the recursive call, Perhaps it made only one, or perhaps it made two, but afterwards it has done some work, some cleaning up work that perhaps is some function of n. You know, perhaps remember from the homework that you were just, or you already submitted, or you will submit this evening, right? There is an algorithm that given all power sets of a set that has n-1 elements, you create a power set of a set that has n elements. And how do you do so? Well, you make a recursive call just to 1, so this constant will be 1, but then you do have a post-processing. You have to take all these strings and all these sets and attach the left out element to it. This term would be 2 to the n in the case of that algorithm, right? Okay, so these costs come up, and you'll see that first of all you have to learn how to deal with these, and these will be an extension that is not hard once you understand the first part. Any questions, you know, so far? Just pipe in. And I'm not, just to FYI, I'm not monitoring the chat, but there is a TA who should be. Okay, just let me just verify. Is the TA among us?
Yes, I'm here.
Yes, Nettie, thank you so much. All right. So you guys have a proof. The TA is among us. Shoot questions on the chat if you want to, and I'll focus on the slides. Thank you, Matt. All right. So okay. So here is an example. And you already know what to do. People give me answers B, and yes. So I was chatting away. Well, most of you have already answered the question. So that is indeed this one, right? And the reason is that it's not homogeneous because there is a term here, but it is linear because, okay, this is a funny constant, but it's still some constant times this plus another constant times the n-2nd element. All right. Okay, so let's try to test how we would do this, right? So here's a bunch of functions. So let's see which one is linear or not. Okay, so the first one, linear, where you can type, I guess not many people were typing, but it is linear, right? All right. Why? Because this is an extra term, but basically you should just look here. You know, is it a linear function of previous elements? And it is. It's some constants multiplied by the previous ones with a linear equation. What about this one? Same, right? Because dividing by 5 is just multiplying by 1/5. So this is another constant. What about this? Yes, it's even simpler. It's just this is the only linear term. And again, you ignore the terms that do not depend on the previous elements of the sequence. The fourth guy, okay, what's going on here? Right? And it is linear, right? Because this is some constant and this is a constant. And you'll refer, look, another change in here is that we are not defining Gn in terms of Gn-2 and Gn-2, 1, right? We're defining them, we're shooting back 2 element backwards and 7 element back, but that's fine. If you insisted that the recurrence relation has to have all the previous elements in some sequence, so if you want to use 7 of them, it has to be Gn-1, Gn-2, Gn-3, Gn-4, Gn-5, Gn-6, and then this guy. Well, it is a case of this, where the coefficients for all the guys who are not here are 0, right? So it is, they are here, they're just, their coefficients are zeros. What about this? Well, no, this is a non-linear term. right? And also this guy is not linear because this is a non-linear term.
But isn't n just a constant though? N is just a constant, right? At that particular iteration.
N is exactly, n is not a constant.
N is not a constant.
No. Yeah.
Okay.
Yeah. So yeah. So yes. N is an argument here. So yes, I see what you're saying. That like it's hard to tell, but like yes, no, n is not a constant here. So homogeneous. Okay, that's easy, right? Like because this term sticks out. Here it does no. Here there is a sticking out term. Here there is not. And these guys are not very important whether they're homogeneous or not, but they are actually homogeneous, right? Because they're nonlinear, so we're not gonna talk about how to solve them. Okay. So here is the general notion of what's a linear and homogeneous recurrence relation. So it's any relation that has this form. You, for some number of d, you define nth term of the sequence in terms of the previous d elements of the sequence, and then you define them in this particular way. So it is a linear function of these d previous elements in the sequence, where there are some constants, proportionality constants. Okay, but it has to be of this form. For example, you saw exceptions from this, right? So in the analysis of fast power, the nth when we compute the nth power of some element, we had a recursive call to computing it for half of n. So this would not be of this form. And what I'm telling you is not really giving you solutions for how to solve these. Okay, so we have seen stuff that does not follow this pattern. Okay, degree d is called the degree of the recurrence relation. Okay, and it will be it's also very intuitive that it's called degree because it will correspond to degree of polynomials you will need to solve to solve these. Okay, so here is the blueprint. When you might remember that when we had these type of recurrence relations, they would translate into geometric series. Why? Okay, just think of this one first. Throw out all these previous ones, all these, right? Fn is some constant, call it c, times the previous one. If you compute this over and over, right, you see, okay, this constant accumulates every time you multiply by this constant. So if you just kicked all of this out, you would have a geometric series right here, right? So what's the solution? It's c to the n, right? It's c to the n. Well, depending on the base condition, but how does it depend on the base condition? In a very trivial way, the base condition just gives you a shift, right? So if the base condition is 1, then the closed formula is c to the n. And for any other base condition, we call it f0, the solution is c to the n times f0, right? f0 is just a multiplicative shift. So maybe it's always like that. Whenever you have a recursion of this type, maybe this will correspond to some geometric series-like expressions. Okay, so so now consider a second example. Throw out this guy and throw out all these. Let's just have this. Is it very different? Not really, right? Because the second element is some constant times the zeros, and the fourth is the same constant times the second, and the sixth is the same constant times the fourth. So you basically have a geometric sequence again, right? But just slower one. you don't multiply by c every time. You multiply by c2 if you jump twice, which means you multiply by square root of c. So that's the same, right? It's just, you know, it's a different power, but it's also a geometric series. So I guess with this hypothesis, you know, if you isolate any of these and kick out the rest, you will have a geometric sequence. So perhaps all of these have a geometric sequence. Well, and that is indeed the case. So solutions have this form. It's Fn is x to the n for some x. They are, so the proper way to read this is that such functions will be solutions, and they are necessary to derive all the other solutions, and all the other solutions are linear functions of these. Okay, so this will become clearer as we go. So let's start. Let's plug in x to the n and see what happens. So let's look at some particular recurrence relation, right? Is this one? Oh, somebody says that their brains leaks out of their ears. I'm sorry. Maybe I talk too loud, or well, okay, or maybe I'm making too much references to too many things. All right, so I guess the message is stick to the program. Take the following recursion relation. Fn is 5, Fn minus 1 minus 6, Fn minus 2. Okay, just some particular example. If your guess was that solutions to this type of recurrence relations are geometric sequences, okay, it's just that you're not sure what the base is, right? Because with these two examples I was sketching on the previous slide, on one base was 2, and the other base was square root of 2. Okay, so let's just, we don't know what this x is. Let's try to solve for it. So what happens if that's our hypothesis for what Fn is? Well, we plug it in, right? So if Fn is indeed xn, then Fn minus 1 would be x to the n minus 1th power, and Fn minus 2 would be x to the n minus 2nd power, right? And if Fn equal x to the n was a solution, then the following would have to be true, right? Because the recurrence relation, the terms of this sequence are bound by this relation. So if these terms are expressible as powers of some x, then whatever this x is, if it exists at all, it has to satisfy this relation, right? So that's a key step, because this might not look like something you know how to solve, but here is the key and very simple thing. Look, this expression contains a bunch of powers of x on both sides of the equation. And what's the common term? It's this one. This term is clearly a multiple of x to the n minus 2. So is this term, right? Because x to the power n minus 1 is a multiple of x to the power of n minus 2. This thing is that times x. And this thing is also that times x squared, right? So each of these terms can be represented as a multiple of this. And now take out that multiple, right? Just divide each side by it. And what do you get? Suddenly you get something that is you should feel comfortable with, right? Because it's just a quadratic equation. So we know how to solve it. Okay, and okay, so now we solve it. This quadratic equation, it has an let's solve for x, right? So this corresponds to like deciding whether that base is 2 or square root of 2 or yet something else in these sketched examples. This equation has a name. It's called characteristic equation. So for a given recurrence relation. So this was an example recurrence relation we had on the previous slide. And we saw that the characteristic equation for it is this. And basically, once you start, you see how this works, that you always stick in. If you see a homogeneous linear recurrence relation, you stick it x to the n to these terms. And if you divide all sides by x to the smallest common power, this falls out. So in fact, you can read off this from those straight away. Just move these guys to the same side, which they become fn minus f5 of these plus 6 of these. And this is exactly the terms of the quadratic equation that you will get. So if you started with the recurrence relation of degree d, you will get a quadratic equation of a degree d. And now just solve for it, right? So, you know, how do you solve for, do you see my whiteboard now, or do you see the screen?
I could see both.
Okay, but the whiteboard is small, right? Okay, so I have to do this, I think. All right. Yes.
Yeah, my question was about the so what you were showing on the linear homogeneous recurrence relation is you were showing that you could change f of n to the form of x of n in order to get like what x actually is. You just have to divide it by the most common term or the least common or like the least common term, and then get your solution, right?
The common term. Yes. Mm-hmm. Yeah, by the highest common term. Mm-hmm.
So what your solution gets is anywhere like which is a multiple of 2 or 3, like any number, right?
I'm not sure. I'm not sure what you just said, really.
So your roots are x is equal to 2 and x is equal to 3. So then what are you trying to prove here? Are you trying to prove like any recurrence relation?
No, this is just an example. Okay, let me do this example on board, right? So fn is 5 fn minus 1 minus 6 fn minus 2. Right, this is my recurrence relation. And now I do basically guess that, because, I mean, it's not a guess, it's an educated guess. We basically know that all the recurrence relations that are homogeneous and linear have equations, all their solutions are of this form, and stick it in and see. So if I do, I get this, x to the n minus first, right? Minus 6 to x to n minus 2. And I don't like it, so I divide by the greatest common term, which is this. And what I was saying before is that x is x squared times this thing, and x n minus 1 is x times this thing. And obviously this thing is that thing by itself, right? So what do I get when I divide? I get x squared is 5x minus 6. right? Then I just move everything to the same side, and this is my equation. So this was my characteristic equation. Okay, now how do I solve these? Okay, well, so this, right? So this equations, quadratic equations of this form, right? So you take a delta, which is b squared minus 4ac, right? And you have three cases. Case one, delta is greater than 0, and so the roots are minus b minus square root of delta over 2a and minus b plus square root delta over 2a, or you have case 2, which is delta is 0, where basically there's one root. So here is two roots. One root is delta falls out, right? Because the square root of it is 0, so it's just minus b over 2a. Or you have case 3, that delta is smaller than 0, and it basically means no roots, at least over reals, right? So because this corresponds to a quadratic equation. So if you look at the graphs of these quadratic equations, right, this would be the case of quadratic equation that has two roots. This would be the case of a quadratic equation that has only one root. And this would be the case of a quadratic equation that has no roots, that does not cross the x-axis at all, right? Okay, so what is it here? Okay, so you know what, you can compute this, but also no, let's look, this has to, if it has roots, then it has to look of in this form, right? Well, perhaps these two roots are the same. That will be the case, this case, but perhaps they're not the same, right? And you can just mix and match. I mean, what are the two numbers which multiply to 6 and add to 5? Yes, and the solution is easy. These two numbers are 2 and 3, right? So if this is indeed x minus 2 times x minus 3, right? If you cross multiply them, you get a 6. Minus 2 times x plus minus 3 times x is minus 5 times x, right? I mean, you can do this by the book, or you can basically guess. So turns out that you have two solutions, which is kind of weird, right? Like you have two solutions to the problem. Solution 1 is fn is 2 to the n. So this is our basis of exponentiation. But oddly, there is a solution 2, which is fn is 3 to the n. And isn't that odd? Like, how can the same recurrence relation, this is the recurrence relation that we started with, how can it have two different solutions, right? If this represents a running time of some algorithm, although it's kind of odd because you would not typically have minus running time, but hey, who knows? Then how come there's two different solutions, right? Like a single algorithm has a fixed running time. It cannot possibly run either in this time or this time, right? Okay, well, because we haven't used initial conditions yet. So that's the answer why two solutions are indeed possible. Any questions on this derivation before I move on?
No, you were mentioning something about having two solutions, but there was nothing wrong with that, right? Nothing wrong with having two solutions, right?
No, well, okay, so I will talk about that later. Okay, if there is no other questions, then I'll just go on.
So this is the recurrence relation that you're trying to prove, right? So that's how you prove recurrence relations, right?
No, I'm not proving a recurrence relation, no.
Oh, you're just showing it right now?
Recurrence relation is not a fact. It's not a proposition. It's gonna be proven. What you might mean is that you prove that a given recurrence relation has a given closed form.
Oh, I understand. So this is what you're trying to prove, like it has a given closed form.
I'm not proving really anything. I'm computing.
Oh, you're computing.
Yeah.
Okay.
It's not a proof. If this is a solution, then for some x, then it turns out that these are the solutions. Okay.
Mm-hmm.
Okay, that's what I'm saying.
Okay.
This is not a proof that. Well, of course, if you stick these back, they will work, right? Because if you just walk back this reasoning, if you stick this thing in here, it will solve this recurrence relation. It will check out. If you stick this thing in here, it will also solve, right? Because this is goes back and forth, all the reasoning. But this doesn't say why are these the only solutions. But they are. But that I'm not saying. I mean, I'm not like explaining that really, why these are the only ones. They are the only ones of this form. But why is there no other solutions of other form? That I'm not saying. Okay. So this was the roots, and therefore I had these two different solutions. Both of them, if you stick them in here, they will work. And how come we have the same? How come this one recurrence relation can have two different correct answers, right? So here is the answer in a way, and not yet. Okay, so the answer is even more. I mean, it's even worse than that. So these are not the only possible solutions, really. In fact, any linear combination of these two solutions also works. So define f of n as some linear coefficient times 2 to the n plus some other coefficient times 3 to the n. These particular examples are of this form as well, right? To get this one, you have to set alpha 1, 1 and alpha 2, 0. And to get that one, you take alpha 1, 0 and alpha 1, 2 and alpha 1, 1 and alpha 2, sorry. This guy is 1, this one is 0, you get that. If this one is 1 and this one is 0, you get that. But you can have any linear combination. So alpha 1, alpha 2 could be 1 and 1 or 2 and 10. Any such satisfies this equation, this recurrence relation. And such combination is called the general solution of the recurrence relation. So let me just show, again, I will not show why these are the only ones, but just that all of these indeed work. Okay. So okay, what was the recurrence relation? The recurrence relation was Fn is 5n minus 1 minus 6 Fn minus 2. Okay, and the characteristic equation x squared minus 5x plus 6, 0 had two roots, x1, 2, and
They
x2,
share the
3.
same
frequency band at the same time. So, but they use, of course, users, most likely users have different.
So, could you say this again? Somebody said something, I did not understand it. Okay, maybe that was some mistake. Somebody unmuted themselves or something by mistake. Okay, so this was the characteristic equation. And so we know that Fn 2 to the n and Fn 3 to the n both solve this recurrence relation. And now I'm saying claim is for any constants alpha 1, alpha 2, if I set Fn to be alpha 1 constant times 2 to the n plus alpha 2 constant times 3 to the n also solves this recurrence relation. Okay, so let's see that it does. Okay, so let's see, right? Is this true? So Fn is this alpha 1 2 to the n plus alpha 2 3 to the n. And if it has solved the recurrence relation, then it has to be true that the nth term is equal to 5 previous ones, which are alpha 1 2 to the n minus 1 plus alpha 2 3 to the n minus 2, n minus 1, sorry, minus 6 times 2 back. And the 2 back is alpha 1 2 n minus 2 plus alpha 2 3 n minus 2. Okay. So let's group it by alphas, okay? Because I have these weird things that I don't even know what they are. It's supposed to work for all of these constants. Okay, so let's group it by this. So let's put all the alpha 1 terms on this side. So then they would look like this. Minus, sorry. Yes, so here you have alpha 1 times 2 to the n. I take this guy and move it to this side. So it's minus 5 2 to the n minus 1. And then, okay, so here is my alpha 1 terms. Okay, let's move them all together. So this would be minus plus 6.
Is that alpha 1 or 2? I can't really see from, okay.
N minus 1. And this is alpha 1. And so this is plus 6 times 2 to the n minus 2. It's 2 to the minus n, it's n minus 2 here, and n minus 1 here, and n here. So I move them on this side. And let's take all the alpha 2 terms and put them on the right. So this is alpha 2. And what do I get? You know what? Let me put them on the same side and just make them 0. So I will also have plus alpha 2, and I have 3 to the n minus, and I put this guy out. So this is 5 times alpha 2. Alpha 2 is here. So it's minus 5, 3 to n minus 1. And I'm left with this guy. So it's minus 6, but I'm putting it on this side. So it's plus 6. Alpha 2 is already here. So I have 3 to the n minus 2. And this has to be equal to 0, right? Because I moved everything to one side. However, so this holds for all alpha 1, alpha 2, because of two facts. First of all, 2 to the n minus 5, 2n minus 1 plus 6, 2n minus 2 equals 0 for all n. And secondly, this thing is also 0. 3n minus 5, 3n minus 2, minus n, sorry, n minus 1, plus 6, 3n minus 2 is also equal to 0 for all n. And why? Because, so first one, how can I tell this? Divide all sides, divide by 2 to the n minus 2. And what do you get? 2 square minus 5 times 2 plus 6 is equal to 0. And that's exactly yes, because x equal 2 is a root of this characteristic equation, x squared minus 5x plus 6 equals 0, right? That was the characteristic equation. That's how we got the solution to begin with, right? So you basically see that this is, it's true for the same reason. And two, well, why is this true? For the same reason, right? Divide by 3 to n minus 2, and you will get that 3 squared minus 5 times 3 plus 6 is 0. And that's yes, because x equals 3 is a root of the same characteristic equation. Okay, so another way to look at it is that if these things are solutions, then so is their linear combination. And because everything that happened here was just linearly combining these terms, and these constants completely didn't matter, they fell out, right? Because these are linear equations, and because these parts are 0, so these two constants don't matter. Our linear way to say it is true for any of these constants. Okay. All right. So the beauty of these linear systems is that you find a solution for something, and any linear combination of these solutions is your solution. Is a valid solution. So this is a good moment to ask if you don't follow, but otherwise I will move on.
So what exactly were you doing on this paper? I just want to make sure, like I know the operation.
I'm claiming, this is my claim. This is what I was doing.
So then you're proving it by a structural induction?
No. The claim is that, no, there is no induction here. The claim is these constants are, okay, well, is this a form of induction? You know what, maybe, but it's...
Because you do have a base case, sort of, right?
I don't.
You don't?
I don't have a base case here. But I will have a base case on the next slide. But there is no base case here, right? It's just saying that any Fn of this type satisfies this recurrence relation. That's the claim. Right? You can set these constants alpha 1 and alpha 2 any way you want. It doesn't matter. Each of such expressions will satisfy this recurrence relation. That's what I was arguing here.
Okay.
Okay. So let's go back to right. So that's the claim I was arguing, that expression like this, which is called a general solution of the will be a solution to the recurrence relation, no matter what the constants alpha 1, alpha 2 are. Okay, so for each of these constants. So, okay, but okay. So actually, cutting to the chase, how are we going to determine these constants? By initial conditions? Okay, because exactly, we have not spoken of initial conditions. We have not spoken of the base case yet. But before we do so, let's try to do this on another example. Okay. So let's not hit the base cases just yet. So let's say this is our recurrence relation, and you know, how would we solve it, right? And again, you guessing that it is a geometric sequence with some base x. So you can express this as x to the n, this as x to the n minus 1, this is x to n minus 2. Then you drop out the highest multiple, I mean the highest common term, which is x to the n minus 2. This comes out here. This remains just 4 times x, and this will be x squared. And then you have a characteristic equation that you will solve, and its solutions will be one of these: 1, 5, minus 1, minus 5. Okay, you know what? Let's do it by so you have a bunch of these, okay, and people try to do it fast on either in their heads or on a piece of paper, and the solutions go over the place, okay, because verbs, yeah, they're not surprisingly, because it's not so easy to solve this like so quick. So so let me just solve it here. So so the recurrence relation is that Fn is 4Fn minus 1 plus 5Fn minus 2, right? And okay, so take Fn to be x to the n, and what do you get? You get that x to the n is 4xn minus 1 plus 5xn minus 2. Then you divide by x to the n minus 2. What remains? X squared is 4x plus 5. And then you move to the other side to get the characteristic equation, right? So this is the characteristic equation for this recurrence relation. And now solve for x. And I can solve in general, right? But I will just try to guess. So what are the two numbers such that these two numbers such that if you multiply them, you get a 5, but you add them, or minus 5, and you add them, you get a minus 4. So one of them is 1 and the other is 5, but it has to be with a minus sign. So it's 1 and minus 5, right? Because 1 times minus 5 is minus 5, and 1 plus minus 5 is minus 4. So it's 1 and minus 5. Solve this, right? So this is the same equation, this and this. Okay, so then therefore the roots are, there's two roots. X1 is minus 1. That makes this 0. X2 is 5. That makes this 0, right? And you can check. Minus 1 works because minus 1 square, 1. Minus 4 times minus 1 is 4. So it's 1 plus 4, 5, minus 5, 0, right? And here would work as well, right? So 25 minus 20 minus 5. Okay, so the general solution is that Fn, so what are the solutions that come out of these roots? Okay, so first of all, anything of this form is a solution. Alternating sequence, sorry, 1 for evens and minus 1 for odds, right? So it's this funny thing, right? 1 and minus 1, alternating between them, right? And the other is 5 to the n. And so the general solution is Fn, which is any linear combination of these two. So it's alpha 1 times minus 1 to the n plus alpha 2 times 5 to the n. And by the way, you can switch them. I mean, there is no notion of first or second, right? Because these are any constants So in particular, you can switch them around, right? So this is just some order that we arbitrarily pick. But there's no notion of so any solution can differ. So it's this guy, right? So B was that answer. So it's just that negative solutions, right? You have to watch out, right? Because the unpleasant thing is that when I have a plus in the equation, that actually corresponds to a negative root, and therefore that corresponds to expression exponential like this. Whereas if I have a term like x minus something, that actually corresponds to a positive root. Okay, so there is like a switch, and if you do this fast, like on a test, okay, you might make a mistake. So just watch out for that, right? It's a very simple thing, but in some sense, if you try to do it too fast, you might make a mistake there. Okay, so what about the initial conditions? Okay, the initial conditions narrow down the possibilities to just one fixed sequence, as it has to be, right? Because it cannot be that the running time of an algorithm is somehow two vastly, completely different, exponential equations are somehow correctly representing a running time of an algorithm, or right, or values of some other recursively defined process. So here was our recurrence relation, and therefore this was our general solution. And now the base case, what are the base cases, right, for this recurrence relation? So it's a recurrence relation that specifies the nth element in terms of the previous two, like a Fibonacci sequence is an example of such, right? So you need two base cases to start this up, right? If you don't declare values of this sequence at two consecutive points at some point, then this will fail to correctly define any sequence, right? So so the base cases have to specify two consecutive elements, and let's just take the starting index to be 0, right? And these initial conditions will suffice to uniquely determine these constants. So I didn't really prove to you that these are the only solutions to this recurrence relation. I proved that all such expressions solve this, but not the other way around, that these are the only ones. But you just, okay, now believe me for a while, right? That is the case, that this is really the only solutions to this recurrence relation. If that was so, then setting up F0 and F1 to any particular values will basically fix alpha 1 and alpha 2. Why is that? Okay, look, if Fn describes any element of the sequence, then plug in N0, and that should compute F0, right? So F0 would be alpha 1 times 2 to the 0 plus alpha 2 times 3 to the 0. But these things are just 1, right? So this is actually just simply alpha 1 plus alpha 2. And if this is indeed an expression that computes every element in the sequence, in particular the first one, then the following would have to be true, that the value of this general expression for n equal 1, which comes out to this, is equal to this value f1. Okay, so and now this is just 2 and this is 3, so you get that, right? And now what do you have? given f0 and f1, any fixed f0, f1 give you two linear equations, linear constraints on alpha 1 and alpha 2. And that suffices to solve for alpha 1, alpha 2, right? So you can, alpha 1, alpha 2 are linear functions of f0 and f1. Oh, sorry for the typo here. It should be f0, f1, both in here and in here. And of course, also for any particular values of initial conditions, right? You can solve this linear system, and it gives you alpha 1, alpha 2, right? So what do I mean here by this linear system, right? So f0 is okay. So this was a different example. So let's go back to this example, right, where we have the general solution was fn is alpha 1 to the n plus alpha 2 3 to the n, right? So this was the general solution. And then we used, okay, f0 is, I plug in zeros here. So it's alpha 1 2 to the 0 plus alpha 2 3 to the 0, which is alpha 1 plus alpha 2. And f1 is alpha 1 to the 1 plus alpha 2 3 to the 1, which is just 2 alpha 1 plus 3 alpha 2. Okay, so look, this is like a linear equation, right? So f0, f1 is a linear equation involving alpha 1 and alpha 2, right? I take 1, 1 here, right? So this is f0 is a sum of alpha 1, alpha 2, when f2 is a sum, but with these coefficients. So it's 2, 3. And so therefore, alpha 1, alpha 2 can be computed. I just take this matrix to this side by inverting it. So I take this matrix and I invert it, and the following is true, right? So that's what I mean, that no matter what f2, f0, f1 are, they will always give you some alpha 1 and alpha 2. And at this point, you will fix the solution, right? So in this case, the inverse of this matrix is, let's see, okay, it's, three. Yeah, 1, 1, another, and here it's 1, 1, 1, 1. No. Yes, just, yes, right. That's the inverse of this matrix, right? So, so alpha 1, alpha 2 is this, right? So for any particular cases, okay, let's take some example. Let's take some example. Let's say f0 is 2 and f1 is 5. Okay, so what is alpha 1, alpha 2 that solve for this particular f0, f1, right? So alpha 1, alpha 2 are 3 minus 1 minus 2, 1 times 2, 5. So 3 times 2, 6 minus 5, that's 1. And minus 2, minus 4 plus 5 is 1, right? So alpha 0, alpha 1 are 1. So the solution which is called particular solution as opposed to general solution, is Fn with these constants. So it's 2 to the n plus 3 to the n. And of course, it's in this form, right? With some particular constants, alpha 1, alpha 0, alpha 1, 1, both equal to 1. And it also satisfies these initial conditions, right? We can compute easily. 2 is 2 to the 0 plus 5 to the 0. So it's 1 plus 1, so it's 2. Great, checks out. F1 is 2 to the 1 plus 5 to the 1. That's 2 to the, no, sorry, what am I doing? It's 3, not 5, 3 to the 0. And here it's 3 to the 1. So it's 2 plus 3, and that is 5, right? So again, I'm hitting both conditions. Let's just do some other initial
Professor, sorry to interrupt you. There are two questions in the chat. One asking about F0 and F1, the other one asking about if we can solve this system of equation as a matrix. So,
could you explain why it is F0 and F1? Did you just choose those base cases? Hold on. Wait, could you explain why it is F0 and F1? F0 and F1 are variable. This is, I'm not fixing F0 and F1 here. It's just for any F0 and F1. For any F0 and F1, this will be the relation, right? For no matter what F0 and F1 are, I can compute alpha 1 and alpha 2 as a function of F0 and F1. And but here I gave a particular example. You know what? Let me write it on a clearer piece of paper, right? So so the recurrence relation was Fn is 5n minus 1 plus, sorry, minus 6 Fn minus 2, and the solution was Fn is alpha 1 2 to the n plus alpha 2 3 to the n. Okay, and I'm saying because the initial conditions have to satisfy it. So the initial conditions are F0 is alpha 1 2 to the 0 plus alpha 2 3 to the 0, which is the same as alpha 1 plus alpha 2. And F1 is alpha 1 times 2 to the 1 plus alpha 2 times 3 to the 1. And that's the same as 2 alpha 1 plus 3 alpha 2. So this is a linear equation. Therefore, alpha 1, alpha 2 are some linear equation of F0, F1. Namely, and I will not rederive this, right? You have to look back at the previous page or just do the matrix inversion. Alpha 1 is 3F0 minus F1. Alpha 2 is minus 2F0 plus F1. And why? Because the matrix 3 minus 1 minus 2, 1 is an inverse of the matrix 1, 1, 2, 3. Okay? So you can solve this in general, or you can solve it for a particular case. So therefore, once you know values of F0, F1, you can compute coefficients alpha 0, alpha 1, and therefore compute the particular solution a particular solution that fits, first of all, the recurrence relation, but that's because it's of this form, right? So for any coefficients alpha, oh God, I'm going from alpha 0 to alpha 1 to alpha 1 and alpha 2. What did I use? I use alpha 1 and alpha 2 everywhere. Okay, so this should be alpha 1 and alpha 2. That fits the recurrence relation, and initial conditions, F0 and F1. Okay, so that's the general blueprint. And now let's do it for a particular case. So example, take an example, F0 is 2 and F1 is 5. If you solve this, then you get alpha 1 is 3 times 2 minus 5, which is 1. And alpha 2 is minus 2 times 2 plus 5, which is also 1. So therefore, the particular solution, Fn, where both of these constants, alpha 1 and alpha 2, are 1, in other words, the particular solution will be 2 to the n plus 3 to the n, solves, number one, the recurrence relation, this one, and fits the initial.
Do we know the exact value of epsilon 1 and epsilon 2? But if we don't, they can just be included in the noise and we have part of the same old
So I think we get some other class like merged into our class.
We are actually simulate this time error.
So somebody is, hold on. Oh, yes. Okay. It was Mehdi. Unmute yourself. Okay. So yes. Okay. So maybe now it's clearer. We can just change the initial conditions and see what will fall out. Okay. Like so. Let's say that you change the initial conditions and F0 is 2. And okay, let's just try something, right? Okay, let's change the initial conditions slightly. We're not changing them by much. What would these coefficients be that fit, right? It's 3 F0 minus F4. So it's 3 times 2 minus F1, sorry, which is 4. So that's 2. And alpha 2 would have to satisfy this, would be computed like this. So it's minus 2, the initial the F0. So it's minus 2 times 2 plus F1, which is 4. So that's actually a 0. So the particular solution that is Fn, which is just 2 times 2 to the n plus 0 times 3 to the n. So this is 2 to the n plus 1. Solves. And these particular conditions, which were F0, F1, which were equal to 2 and 5. And this new function, right? So this was the solution for this recurrence relation with these initial conditions. And this new thing is a solution to the same recurrence relation, but different initial conditions. And it fits in its initial conditions. What were they? F0, F1 equal to 2, 4. So you see how dramatically that stuff is sensitive to the initial conditions, right? But you have seen this before, that if you set up the initial conditions on some, strange recurrence relation, the behavior of the rest will vary, will be very determined, right? if you take a Fibonacci sequence and don't start it on F0 and F1 the way Fibonacci did, but just change, you know, like F0, take F0, take F0 1 and F1 0, okay, and watch what happens, right? Or if you make big changes in these, I mean, in the initial conditions, the sequence will behave very differently, right? So you can just, I didn't do this, so I don't know what particular condition would be such that only this term will be left out, right? I mean, so in other words, what are the initial conditions so that this is the answer? But well, actually, that is simple to write. You just have to plug in this value and see what the initial conditions are. So if we took if we F0 was 1 and oh, well, I can do this. F0 is 2 and F2 is 6. Sorry, F1. Sorry, F1. F0 and F1. Because there are 3 apart. So this should basically be this sequence, I think. But although who knows? Let's test that. Alpha 1 is 3 of this minus that. So 3 of 2 minus 6. And oh, yes, indeed, that made alpha 1 to be 0. So this term will drop out. And let's see what term. Okay, well, you can guess what term. It's 2. So alpha 2 is minus 2 of these guys plus this guy. So it's minus 2 times 2 plus 6, indeed 2. So the particular solution is Fn 2 times 3 to the n, right? And this solution again solves, first of all, the same recurrence relation, but also fits the conditions that F0 and F1 were 2 and 6. So sort of, by coincidence, but beautifully, tiny difference in these initial conditions, and you vary between pure exponential 2 to the n with base 2, pure exponential geometric sequence with ratio 3, right? The initial condition is 2 in both cases, right? Well, because indeed it is 2 in both cases. So this, no, I mean, you can sort of look, if you look at these initial conditions, you can see straight away. You start with 2 and the factor is 2. Well, of course, this is the solution, right? You start with 2 and the factor is 3. Well, this is the solution. But you start from 2 and the factor is, neither of these. It's neither 2 nor 3. It's a combination. It's a linear combination. Okay, so I have some more examples on the slides, and of course there is more examples in the book and some participation activities that guide you through these. What I have not covered is how to now add the non-homogeneous term. Okay, so what do you do when these equations have some sort of non-homogeneous term, right? Plus 1 plus n plus some other function basically of n in general, and it's not hard to extend it to that case. Okay, we will not. I will not. This is not on the homework, but you should know how to do that. I mean, it will happen. Just see how this is extended, because okay, it will be a useful thing for you in the future. All right, that's all I have. Are there some questions?
Yeah, Professor, can you hear me?
Yes.
On the sheet that you're currently working on, Going from the inverse matrix to the equations A1 and A2, could you just visually show that on the paper?
Hold on a second. Alpha 1, alpha 2.
You see how it says, namely, alpha 1 equals 3f0 minus f1? In the middle of the page.
Yes, yes, right. Okay, you know what? So, you know, so some of you, you know, have some linear algebra background where you can compute, basically show these inverses of matrices, and it's easy for you then. And some of you do not. And but basically, I think everybody knows how to solve a system of equations when, okay, here is a system of equations. These are given, and the unknowns are here. And you have two unknowns, alpha 1 and alpha 2. And you have a linear relation, two linear relations, right? You know how to solve these. Just forget about the matrices, it doesn't matter. For any values here, you have two linear equations on two unknowns. So you just solve them for alpha 1, alpha 2. That's all that is happening. Given f2, f0, f1, I solve for alpha 1, alpha 2. I solve it using this general equation, this, which I derived because of the linear algebra, but you don't need to. If you were given f0 and f1, just look at this system and solve it for alpha 1, alpha 2. Any method you like. Do you see what I mean?
Yeah, so we can just take the inverse of any matrix and then just make it into a system of equations.
Yes, if you want to be general, but in fact, like every question that we will ask you does not it does not ask for this generality. We will give you, okay, there will be two types of questions. Here is the recurrence relation. Give us the general solution, and here is the particular initial conditions. Give us the particular solution that fits those conditions. Right?
All right. Yeah, that makes sense.
All right.
All right, thank you.
I have a question. We don't have to worry much about matrices for this class, right?
No.
Okay.
No. What I was just showing is that you can look at it that way, and then you will see that indeed for any f0, f1, you can compute alpha 1, alpha 2 fast, but you can also compute them a little more slowly without thinking of matrices. Just solving this type of two equations with two unknowns. It's a system of two equations with two unknowns. Okay. Yes. So there is a comment that is hard to follow. Yeah. So. You know, I have the slides on this, so I will post these slides. The slides, you know, have some of these examples, not all of these examples, and I think a still picture of these handouts is also better than the camera. Okay. So I'll see you all later. You know, start working on homework 5 soon. There is, yes, exactly. So I will scan these uploads right now and upload these right now. Okay, and the problems on homework 5 are you know, you have to think about them, you know, I mean, okay, so you have to think about problems in general, right? But like, I think in particularly in this topic, they're just not automatic. There is no, okay, here's the method, boom, I have a solution. You know, I just follow the blueprint. It is, it requires more thinking than that. So the solutions, once you see it, is not hard, but it does require some thinking. And okay, so start earlier. Our proofs that our algorithms work should be more so in words. Yes. Algebra, no, not much. You know, just no. There is barely any algebra. Yes, like just some sort of symbol adding. Yeah. Okay, I will